Hi, my name is Youngseok Kim, PhD candidate in KAIST, and I'm happy to share my work today. The title of the presentation is Craft Camera and Radar 3D Object Detection with Spatio-Contextual Fusion Transformer. I have done this work with my colleague Sanmin Kim and my advisor Dongsuk Kim and co-advisor Choi. I will start the presentation with the background and motivation of camera and radar fusion. So why do we choose camera and radar instead of using LiDAR? As we all know, LiDAR is preferable sensor for autonomous driving system because of its accurate, precise, and dense data. However, typical LiDAR have many moving parts, so LiDAR have a reliability and maintenance issues. And of course, it's still far expensive for commercial vehicles. On the other hand, camera and radar are already widely used for ADAS thanks to their many suitable properties for mass production. However, driving environments of ADAS using camera and radar have very limited to non-complex environments such as highway. So if we could achieve the LiDAR level performance with low-cost camera and radar sensors, we believe it will have great impact in many fields. But why camera and radar fusion is difficult? Typical sensor fusion for ADAS use the late fusion or object-level fusion strategies that fuse the final detection result at the last stage. Of course, it has advantages that separately developed algorithm can be integrated at the car maker company level. However, we cannot expect the high performance improvement by late fusion because we lost many valuable information if we only use the final prediction results for the fusion. On the other hand, our method use early fusion strategies that fuse the feature level information at the intermediate stage. This early level fusion is able to maximize the potential of each sensors by fusion. The next motivation is how to fuse two modalities. In ideal case, both information of multimodal inputs are informative and helpful for detecting some object. However, in the real situation, only one of the modality can be informative and the other cannot be. The proposed fusion framework aims to handle this kind of situation and make the best of both modalities, even one of the input data is not helpful for the fusion. And the last motivation is what information to fuse from camera and radar. As can be seen on the right figure, camera and radar have very complementary characteristics, so we can expect more performance gain by fusion. And more specifically, in terms of the spatial properties, the camera provides dense angular resolution, but image cannot provide this distance or depth information. On the other hand, radar can provide long-range distance measurement in radar direction, but its angular resolution is very low. In terms of contextual properties, camera image can provide rich semantic information, while radar cannot. As the pros and cons of camera and radar are very clear, we focus on fully utilizing the spatial and contextual properties by well-designed fusion module. The proposed method have two-stage architecture. Given 6 surrounding images and radar points as input, we first predict the 3D object proposal using lightweight camera-only 3D detector. And after that, we extract radar point feature and associate radar points around 3D image proposal with a soft polar association. And after that, we use consecutive cross-attention modules to exchange the spatial and contextual information from camera and radar features. And finally, the fused object features is refined to output more accurate final prediction. In summary, we thoroughly investigate the characteristics of camera and radar, then propose soft polar association and spatio-contextual fusion module to effectively fuse two modalities. And our method achieves state-of-the-art results on nuScenes dataset and even outperforms LiDAR detector point pillars. First, our monocular 3D detector uses CenterNet-like architecture. The CenterNet defines the 3D object detection problem as the 2D center point detection plus depth estimation problem. If we detect 2D centers of object and its distance, its 3D location can be calculated using simple perspective geometry using this equation. and we extract this Sentinel-like architecture with few modifications to predict more accurate depth and its uncertainty. Note that the proposing a 3D camera detector is not the main contribution of this paper, and refer to this paper if you are interested. So now we have 3D predictions from the camera-only 3D detector. And more specifically, we use the 3D prediction results as a proposal for the following stages, and we not only use 3D bounding box, but its features at the center point. And after that, we extract point-wise radar features using PointNet. And the next step is to associate image proposals and radar points considering its spatial properties. We first analyze the error distribution of image detector in Cartesian coordinate system. And understandably, we can observe a huge localization error in both x and y directions. However, if we transform the coordinate system into polar coordinate system, we can see the most error comes from the radial direction, while azimuthal direction is relatively small. It means that if we transform the coordinates from Cartesian to polar, we can effectively reduce the source of localization error in one direction, which can make the problem more easier. Now, we can focus on reducing the error in radial direction to make the localization more accurate. To do that, we first transform the image proposals and radar points into polar coordinate system, then translate the origin point of the center of image proposal. And now, the regression target between image proposal and the ground truth becomes the offset in range and azimuth direction instead of x and y. And after that, we associate radar points around the image proposal using ellipsoidal shape threshold, considering the image proposal has a huge localization error in radial direction. Specifically, given a set of image proposal bounding box and radar points, we use the most left and right corner of image proposal 3D bounding box for azimuthal threshold. And for the radial direction, we make our monocular 3D detector to estimate the uncertainty of localization error in radial direction. So if the image proposal has the high uncertainty in radial direction, our threshold becomes large, so it can associate radar points from a longer distance, which specifically up to 5 meters. And after associate radar points, we predict the offset in the same polar coordinate system. And then we transform it back to Cartesian coordinate system to get the final prediction results. So the soft association in polar coordinate system maximize the potential of fusion given inaccurately predicted image proposal, specifically in radial direction. And the next step is to fuse the information between image proposal and radar point feature using Spatio-Contextual fusion module. In this module, we first project each single radar point into image view and gather image features around the projected radar position. As we want to encode the image feature to the radar point, we use the radar points as query and image features as key and value, and we use 2D positional embedding. We follow the conventional self-attention, cross-attention, and feed-forward network order from the transformer, and we adopt pre-norm technique, which use the layer norm before the attention operation for the fast and stable training. In addition, we designed an auxiliary task and loads to train this module more effectively. We add shallow MLP layers with a sigmoid activation at the last layer and make it to predict whether radar points is inside of 3D bounding box or not. By doing this, radar points become more able to distinguish which radar points is from the object, which we have to utilize more, and which points belong to the background, which is not informative for fusion and we have to ignore. We visualize the attention weights of deformable cross-attention layer here. As can be seen, the attention module put more weights around object center than background as the layer goes deeper. Our next goal is to refine the image proposal to be more close to the ground truth center. Now, the image proposal features become query and radar points feature around the image proposal becomes key and value. we use the same transformer layer as the previous slide, but we use the 3D positional embedding in polar coordinate system instead of 2D. Given output of cross attention layer, we use few MLP layers to output location offset, velocity, and scores. Finally, the predicted object center is transformed back to Cartesian coordinate. We visualize the attention weights where the image proposal see more for the fusion. On the left side, black, red, and blue box denotes the ground truth, image proposal, and fusion results. And the line between image proposals and radar points shows the association with each attention weight. As the layer goes deeper, our attention module ignores points from the background and we put more weights to the foreground points. Therefore, the refined center can be more close to the ground truth center. And for the experiments, we conduct the experiments on the nuScenes dataset. First, we compare our method with the state-of-the-art method using single frame and trained with nuScenes dataset only. Ours outperforms all published methods with a large margin, and we highlight that our method only requires 30 milliseconds of computational cost for significant performance gain. Also, the performance gain by radar fusion over camera baseline is much significant compared to the previous camera radar fusion method, center fusion. In this video, red, blue, black box denotes the image proposal, fusion results, and the ground truth. A red circle highlights the case where the object does not have radar points returned due to occlusion by building and wire defense, but our method successfully detects them using camera only. Also, blue circle highlights that image proposal with high localization error becomes more accurate by our radar fusion. Note that we did not use the temporal information such as sequential input or tracking. Our method also works well in rainy scenarios where the performance of LiDAR only method may be degraded. Finally, our method also works well at the nighttime. At the nighttime scenario, we found that the camera-only method has a larger localization error, and our fusion can have much better localization results. In conclusion, we can say that our method achieves the first state-of-the-art performance by camera and radar fusion, and ours shows significant performance gain over camera-only baseline with a marginal computational cost, and also it shows the robust performance in various environments. Please check out our paper for more information and feel free to ask a question if you have. Thank you.